A 1.6 kilogram rock, and it's going to be dropped from a height of 15 meters. So imagine it's perched on a ledge or something, or a cliff that's 15 meters above the ground. So the rock might start from here, from rest. V initial is 0. And as it falls, obviously it starts to gain speed, gain velocity. And we want to know what the final speed is just before it hits. Now we know how to do this with kinematics, V initial is 0, etc. We know how to do all that. We're trying to do this with energy now. And according to the law of conservation of energy, if I add up all the initial energy, all the energy before, that number has to remain constant. All the energy after has to equal all the energy before. You can't create energy out of nothing. As long as the system is closed, in other words, as long as nobody comes in and pushes that ball halfway down. So we're just leaving it as we see it. So we just itemize. My total energy before consists of just potential. It doesn't have any kinetic because it's not moving. And then just before it hits the ground, all of that potential got converted to kinetic. And I no longer have any potential because I'm as low as I can possibly go in this question. So I started with only potential energy at the top, and it all converted into kinetic energy at the bottom. You can almost think of this equal sign as similar to being converted to. My initial potential energy is converted to kinetic. So then we just plug in our formulas. Notice that the mass of the rock actually doesn't matter. There's an m on both sides. They're gone. And when I solve it for v, if I multiply both sides by 2 to get rid of the 1/2 and take a square root, I end up getting a final speed just before it hits of 17 meters per second. So just like your kinematics equations, mass does not matter, and our final speed just before it hits is 17 meters per second.